The second half of chapter 2 really focuses in on this concept of a normal distribution, which a lot of variables will follow this distribution where you have that peak in the middle. But when we say something follows a normal distribution, we mean some very, very specific things about it. But one of the important things about this is that a good bit of the statistical inference that we do in this class, in fact, most of it, is based on the fact that a variable will follow a normal distribution, or at least fast forwarding to some vocabulary we haven't locked in on yet and won't for a few months, but the fact that the sampling distribution of a random variable follows a normal distribution is very, very useful to us. So one of the characteristics of the normal distribution is that it follows this 68, 95, 99.7 rule. I usually just throw the numbers right out there, 68, 95, 99.7. It's also called the empirical rule. Okay, so what we're seeing here are a distribution of batting averages for Major League Baseball players, and we can see somewhere around the middle where they could report to us what the mean and the standard deviation are. And again, just because we have the mean and standard deviation for a variable does not mean that the variable follows a normal distribution. So here they're showing us, the proportion of players who have averages in a particular window, and they're using the red to shade it, right? In the first graph below, the bars in red represent the proportion of players who have batting averages of at least 270. So they're shading those bars in. What you start to find is that we can we can forget about the histogram and the bars and just look at this as a normal distribution curve altogether. So let me scroll down, and they're shading that in, but we don't have to see the histogram in order to start to answer these questions. So here we have the same alternate example. They're telling us the batting average, or the center of this normal distribution, is going to live at 261, and the standard deviation is 0.034. So the first part says, and we'll let the textbook authors do that for us. They're just going to sketch a normal density curve for this distribution and label the points that are 1, 2, and 3 standard deviations from the mean. So notice what they've done. They put the mean here, and then they add 0.034 to get to 0.295, and they subtract 0.034. Okay, then you add 0.034 again, which will put you here at 0.329, and then you subtract 0.034. So each one of these movements is adding, subtracting a standard deviation in each direction. So the first question here is, what percent of batting averages are above 0.329? So we're looking for this shaded area, and we can actually use the empirical rule for this. Okay, because this is 2 standard deviations above the mean, I can figure out what that area is using the 68, 95, 99.7 rule. So let me just back up for a second. The 68, 95, 99.7 rule means this. If I go 1 standard deviation above and 1 below, that's 68% of all of the data. Okay? If I go 2 standard deviations above and below, that's 95%. So if we go from here to here, that's 95% of all of the data. Okay? And then finally, if I go 3 standard deviations above and below, that's going to be 99.7%. If we're following a normal distribution, it's not true for any variable, but if we know the variable follows a normal distribution, it should follow that empirical rule. So let's go back to answering this question again. Above 0.329. So we can see 0.329 is 2 standard deviations above the mean, right? Well, remember what's happening here. 95% lives from 2 below to 2 above. So if we take 100% minus 95%, leaves us with 5%, right? That gets divided into 2 tails. So what percentage would live above 0.329? About 2.5%. Okay, and that's just using the 68, 95, 99.7 rule, right? We're gonna start to lean on our graphing calculators to answer these questions, but if it's a specific number of standard deviations above or below, then we won't need a calculator. We can just use that 68, 95, 99.7 approximation. So let's take a look at the next one now. What are they looking for here? What percentage are between 0.193, so that's going 2 below, up to 0.295, and that's only 1 above. So I'm going to partition this in a particular way now, all right? I'm going to come right up the middle here. We know this is the 50th percentile, right? 0.261 is the mean. So if I went, try to picture this with me for a second, and then I'll come back to it. Hopefully you'll follow along with me. Remember, what percentage lives here? In here, 68%, right? So bear with me then. What if I only wanted to go 1 above? So I'm just going to go right from here to here. That's that sliver. That's going to be 68% divided by 2. That would be 34% in this slice. That's 34%. See it? Okay, now the other part of this question that they asked us was to go down to 2 below. We go down to 2 below. So that's going to be 95% divided by 2. So that's how I would go about answering this. I would look at those two partitions. One of them is half of the 68%. The other one is half of the 95%. And that to me would be a pretty easy way to, let's get rid of this. So to answer part C, I would take 0.95, divide that by 2. That is this portion. And then I would take 0.68 divided by 2, or 34. Okay, that is this portion. And that's what they're asking for, from 0.193 to 0.295. So I get 0.815 or 81.5%. This is just using the 68, 95, 99.7 rule. We are going to get a little bit more sophisticated now. So this is a copy of the formula sheet that you are given when you sit for the AP statistics exams. This is the most updated version of the formula sheet. And you'll notice you start to have some tables of values. So this first table is a table of z-scores in a normal distribution. And what it tells us is, like, I'll pick one that, should make sense. For example, if your z-score is 0, right, that means you live right at the middle of the normal curve. And this gives you the area below that. So when we look at this curve, the area below 0, a z-score of 0 would be 0.5. That should make sense to us, okay? So now what happens, what if my z-score is -1? Like I'm 1 standard deviation below the mean. Now maybe you could picture that would be 32% divided by 2, right? If I go 1 standard deviation below to 1 above, that's 68%. So what's left? 32%. And then we could divide that into the two tails. So it should be about 16%. So let's see, a z-score of -1 has an area to the left of, now this is a little bit more precise estimate, it would be 15.87%, 0.1587, not just straight away 16%. But this is a more precise estimate. So your textbook authors will show how you can use this table and these z-scores to make these calculations, but I want to lean on the calculator for it, okay? So when we go back to our examples here, find the proportion of observations from the standard normal distribution that are between -0.58 and 1.79. So the first thing I'm going to do, they're showing how to use the table to do this. I'm going to go ahead and I'll sketch a normal curve so hopefully you can picture it. And I think, for full credit on an AP exam, they ask that you do that. Your quizzes for me are going to be in Schoology, so it's going to be kind of hard for you to draw sketches. I'm trying my best to create questions that help me see your conceptual understanding, but don't require that you have to draw or sketch anything for me, if that makes sense. So I'm trying to avoid those. In a world where you could do everything on paper for me, it might be different, but we're not going to go that route. And then I'm going to come up to 1.79. So this is not something that the 68, 95, 99.7 rule can do for me, right? It's not an even number of standard deviations above or below the mean. We're dealing with decimals. So I'm going to go to the calculator. You have an option on your calculator that will do this for you, okay? On your calculator, I want you to find the second key and the variables key. Underneath, up above variables in blue, you're going to see distributions. So there's a couple of very specific distributions we'll study in here. The normal distribution for sure is one of them, the binomial distribution. So we're going to use this key. I want to hit the second key and then my variables key, so it takes me to my distribution menu. Okay, this first option here, normal PDF, if you could just delete it from your menu, that would be terrific. We never, ever, ever use that. So we're going to use normal CDF. It's a cumulative distribution function. And what this is going to ask you for, first of all, is your lower limit. It's automatically set at negative infinity, but look at this is why I always draw the graph first. My lower limit is negative 0.58. So be careful to use the negative button here, not a subtraction symbol. I want to put in a negative 0.58. That's my lower limit. And then what's my upper limit? Trying to grab this and slide down. 1.79. So if you draw it on the graph, you'll be able to see what your lower and upper limits are. And this is a z distribution, so the mean and standard deviation, of course, are 0 and 1. It's a standard normal distribution. So you might have a screen that just looks like this. It's lower limit. The syntax is always going to be lower limit, upper limit, mean, standard deviation. Okay, so whenever you use normal CDF, that is the syntax. It goes lower limit, upper limit, mean, standard deviation. And it's pretty close to this 68%, like one standard deviation below to one above. Well, I only went about half one below and more than one above. But so we get 68.2%, 0.68 or 68.2. Either answer is acceptable. They both mean the same thing. Okay. Now let's look at the next question. They ask a little bit different framing here. Working backwards. In a standard normal distribution, 20% of the observations are above what value? So let's think about that. They're basically asking us for the 80th percentile, right? The mean of a standard normal distribution is 0. Not a great curve by me, but they're basically saying here, what z-score? So I don't know the z-score, but what z-score would live here so that the area above it is 0.2. Okay? So this is not what we've done previously. What we had done previously was lower limit, upper limit, and we find an area in between. So if you take a look at the same menu on your calculator, if I hit second and the variables key, you're going to see the third option is inverse norm. So the way inverse norm works, and some of you might have calculators that do it a little bit differently where you can tell an area to the right. If your calculator allows you to do that, then you can use 20% here. Okay, the area that I'm talking about here, at least that I want to tell the calculator, is the area to the left. So anytime you use inverse norm, it's going to be area to the left, mean, and standard deviation. So my area to the left here is 0.8, and my answer should make sense. If I put in the wrong area, if I put in 0.2, I should get a number that doesn't make sense. 0.84 makes sense to me here, right? 0.84 is a z-score above the mean. If you put in inverse norm and you did this wrong, and you draw the picture, you should be able to catch your mistake. Suppose you weren't aware that it's area to the left. That's the syntax. This shouldn't make any sense. There's no way negative 0.84 has 20% area to the right of it. It would have more than 50% of the area above it or to the right of it. Okay? So now we want to graduate one step further. Instead of just looking at the z-scores, we can use raw scores as well. We just tell the calculator what our mean and standard deviation is. So here we have tennis pro Rafael Nadal, and his average serve is 115 miles per hour. Assume that it's normally distributed. That's huge. We can't do anything with this. They don't tell us that. And then he gives a standard deviation of 6. What percent of his serves would exceed 120 miles an hour? So I'm going to go ahead and draw Nadal's normal curve. I'm going to have 115 living in the middle. And they want to know what percentage of his serves are going to go up above 120 miles per hour. We know it's possible just because they average 115. That means some are faster than that, some are less than that. So I want to know what proportion that is. So this is just normal CDF. Lower limit is 120. The upper limit, this is where it gets kind of tricky. We just have to pick a big number. 6 is your standard deviation, so truthfully, like 150 is probably plenty big enough. But I went 120 to 500. You could put 5,000. You could put 5 million. It won't matter. Now I put in the mean of 115 and the standard deviation of 6. So it's very, very important that we have the right mean and standard deviation here. Again, remember, it's lower limit, upper limit, mean, standard deviation. And let me just reiterate the upper limit piece here. If I hit second enter, And like I was suggesting before, instead of 500, what would happen if I inserted a couple of zeros here? Absolutely nothing, right? It's going out, infinitely small out there, so you get the same answer either way. Now, where you could go wrong is if you didn't pick a number big enough. Like if I only put 130 here, that might not be high enough to get a precise answer. So about 20%, 20.23%. Okay. What percent of his serves are between 100 and 110? So let's sketch that out. Remember, 115 lives in the middle here. So 100 would be here. 110 somewhere here. And again, it's another normal CDF problem, okay? Except this time our lower limit is 100 and our upper limit is 110. So I can just hit second enter, and I'm just going to back up and change the 120 to 100. Get me back in there. So 100 is the lower limit now. Now the upper limit is 110. And I can delete some of this other stuff. Yep. And then I need a mean of 115 and standard deviation of 6, still the same. So 0.196. So that's how we can do it if we don't have a mean of 0 and a standard deviation of 1. We just tell the calculator what they are. Okay, so according to cdc.gov, heights of 3-year-old females are approximately normally distributed with a mean of 94.5 and a standard deviation of 4. So let's first and foremost go ahead and try to picture that. I'm going to throw 94.5 in the middle here. And I want to know, what's the third quartile? Well, where's the third quartile? That's the 75th percentile. That's what they're asking. So they want to know, how tall is this person, so that 75% or 0.75 of all others, females, are going to be below that. So this is an inverse norm question. So we would inverse norm 0.75. Remember, it has to be area to the left. And then we just tell the calculator our mean is 94.5 and our standard deviation is 4. Okay, and then we can paste 97.2. And we want to include units there, so we keep that in context. 97.2 centimeters would be good. So another obvious question we might want to ask is, do we have a set of data that follows a normal distribution? Okay, so here you have a list of numbers here, and if we make a histogram and we calculate the mean and the standard deviation, we could look to see if our data follow the 68, 95, 99.7 rule. So that's what they've done. They add and subtract a standard deviation to get this interval, right? They took 15.825 and subtracted 1.217, and they added 1.217. And then they just go back to the histogram here and just count how many numbers fall between 14.6 and 17. They count them up. This is kind of a brute force, long way to do this. But it's close to 68%. This is close to 95, and this is close to 99.7. A little bit better, more efficient way to do it is here. This is a normal probability plot. This is going to plot, and it could put the z-score on the x-axis or the y. It really doesn't matter. But what this does is it plots your z-scores versus your raw scores. If this type of scatter plot is roughly linear, then we know that we're dealing with an approximately normal distribution. Your calculator will do this. If I go to stat and edit, so here I have a list of numbers in here. Not really quite sure what that's from, probably a previous example. Doesn't really matter. I'm going to go to second y equals, and I'm going to turn plot 1 on. And then your normal probability plot is this one here. It's the very last one. So when I go to plot type, I'm going to arrow over there. and press enter so it's highlighted. And remember, my shortcut for getting the graph window is always zoom 9. Okay, so it looks like roughly linear pattern in that normal probability plot. We have no reason to suspect that data doesn't follow an approximately normal distribution. So what would you expect to see if the data is not a normal distribution? Look, long tail to the right, that's a skewed right distribution, right? So what happens? This guy here has a really unusually large z-score, right? And it's going to show up on the plot like this, and you can see that its curve is kind of bending, and then we have that large outlier, which would lead us to believe it's skewed to the right. If it went the other way and it bent back this way, that would lead us to believe we probably have a skewed left distribution, a really low number, okay? But you can see when the normal probability plot doesn't follow a linear pattern, right? This is not a straight line. It really looks like it's bending here. Then our data, we don't want to assume the data follows a normal distribution.